Dear learners, we are in module 4 of week 1. So before we are going to start today's topic, let us first see what are the things that we have learned in our last module. In our last module, we have seen how assignment works in digital computer. We have given certain example and we have seen how it is getting executed inside the memory or processor. And next point, we have also understood the round of error, which is a very common issues in digital computer, and as a result of this rounding of error, the exact match between two real numbers is also not possible in the machine, and we have seen that using a tolerance value to compare two real number in the case of Babylonian search algorithm. Now in the next topic, this module, what we will discuss a new algorithm and its issues, which is very famous Euclidean algorithm, by which we can find the GCD of two numbers. Let us now see the algorithm for finding GCD of two numbers, m which is greater or equals to 0 and n which is greater than 0. Okay. As before, let us start with a specific example. Suppose m equals to 186 and n equals to 84, and the GCD, which is initially unknown, is x. Now what is the definition of the GCD x? X is the largest number which divide both 186 and 84. Okay. Now let us take an example of a rod AB of length 186 unit and another rod CD of a shorter length 84. And now let us first check whether x, the value of x, can be 84 or not. To do that, let us first cover the longer rod AB with the help of the shorter rod CD. Okay, we place CD one after another on the longer rod AB. So first we cover the first one, AB. So this is what AP, and the length of this will be 84 unit. So we still have remaining length, so we can cover more shorter rod. So this is the second one, PQ. Again this is 84. So now we have covered up total 84 plus 84, 168 unit. There are still pending 18 unit, but if you see the 18 is less than 84, so in this length we cannot actually cover any more CD, so the length 18 will be remain as it is. So what we have finally found is that you cannot cover up the entire AB with the help of CD. You will get some length which will be available, it cannot be occupied. So that means if you say in terms of algebra, when you divide 186 by the number 84, then you will get a remainder 18. So 18 will be remainder, right? So if the remainder is a non-zero, then we can say that 86 is not divisible by 84. So we can conclude x cannot be equals to 84, but x must be something which is less than 84. From definition of the GCD, we can also say that number 1, x divides the length 186, which is nothing but the full rod AB. Okay, and number 2, x also divides 84, which is the length CD. Now from the statement 2 we can infer x divides 168 as well. Why? Because 168 is nothing but multiple of 84. That means if you see the diagram, 168 is the length of AQ, right? So now from the diagram we can simply write that AB, that is equals to AQ plus QB, right? Now AB minus AQ, that should be is equals to your QB. Then from here we can write it, right? So now AB, which is divisible by x by 0.1, and AQ, that is also divisible by x by this argument. So that means this whole quantity AB minus AQ is also divisible by x. That means the QB is actually divisible by x. So this implies QB is, or rather I will write x divides QB as well. X divides QB as well. Now what is QB? QB is nothing but the R. So from the definition of the GCD, x divides 186, x divides 84. Together these two implies that x also divides QB, or remainder of 186 and 84, right? So this is very interesting property. So what we can say from this place, x is the largest number which divides 184, 186 and 84. So x is the largest number. X divides 184 and 84 both. That implies x divides 18 as well. That is 18 means 184 congruent and modulo operator 84. Modulo operator means it will provide you the remainder. So if x divides 184 and 84, then x also divides the remainder 18. Okay, now how we get this remainder? Just by dividing 184 by 84. Okay, so what we can see here, x is the largest number which divides both 84 and 18. We started with x is the largest number which divides 186 and 84 from the definition, and from this we have proven that the same x will also divides 18. So we can write x is the largest number which divides both 84 and 18, right? So what we can do here, we can cut this 18 and we can argue that x which divides these two numbers, the same x also will divide this number as well. So what we can say, the GCD of this number and this number is equal to GCD of these two numbers, right? Because x divides both of these two numbers, CD and the 18 and 84 as well. So if x is the GCD of these two numbers, then x will be GCD of these two numbers as well. So what we can conclude here is that GCD of 186, 84 is same as GCD of 84, 18. So we can write it like this: GCD of m, n is equals to GCD of n, m percentage n. See here, this is what your m and n, okay? And so in the next iteration, what will happen, this n will come here as a first argument and the second argument will be m percentage n. So this formula we will be repeatedly using in further process. So therefore now next what we need to check, value of x equals to 18 or not. Okay, how do we check that? So we will divide the length 84 by 18, and if you get any remainder, non-zero remainder, that means 18 cannot divide 84, so 18 cannot be value of x. Now same thing, how we can see, let's try to cover the larger length CD using the smaller length EF. Okay, so this is the first one, so it will be 18, and this is the second one, again 18, this is the third one, again 18, this is the fourth one, again 18. So total we have covered up to 72 unit of the area. So remaining 12 unit of the length we cannot cover because the shorter length EF having length 18, which is 18 is higher than 12. So therefore here as well I am getting R equals to 12. That means there is a non-zero remainder. So even X cannot be 18 anymore. Now by the same argument we can say that if X divide EF and CD both, then X will divide also the remainder when we divide CD by EF. So therefore we cut that remainder and we will say that now X is the largest number which can divide these two. So X is basically the GCD of EF and the shorter length GH as well. So therefore now the problem is even become smaller, and now we need to find out the GCD of these two numbers. By the same way, what we will do, we'll try to cover the longer rod. So this is 12. So the remaining 6 you cannot cover by the length 12. So here as well, even your value X cannot be 12 because 12 cannot divide 18 because we are getting a non-zero remainder. So even 12 cannot be the value of X. So therefore we should proceed. So we will argue X will divide 12 as well as the remainder when we divide 18 by 12. So therefore this remainder will come in the next section, let's say, which is Ij of length 6. Now let us try to cover the length GH using Ij. So then you can cover it by 2Ij, right? If you place the rod of length Ij 2 times, then you will cover the entire 12 units. So therefore in this case R equals to 0. So that means we can say that 6 will divide 12. So therefore 6 will be the GCD of these two, 12 and 6. So the value of X equals to 6 here, right? Because the moment you get a 0 remainder, that time the divisor will be treated as the GCD of that two number. So now go back to the reverse way. So now we receive that X equals to 6 means 6 is the GCD of these two numbers. Again, we have earlier proof the GCD of these two is also X. So, and GCD of these two is also X, and GCD of these two is also X. So therefore 6 is the GCD of the two number 186 and 84, right? So we can say here this is what our GCD. Now there are few things you need to notice. So here how many iterations we are doing? This is the first iteration, this is the second iteration, this is the third iteration, and this is the fourth iteration. And here we have 3 quantities. So iteration 1, okay, we have the value of M which is 186, okay, and the value of N is 84, and this is what my 18, right? Now you can observe one interesting thing here. M is always greater than N, and of course R is, since it is the remainder, it must be less than M and N both, right? Now that's what in the length also you can see that this is what your M 186, this is what your N, and this is what your R. Now in the next iteration the value of the M will be the value of the N in the previous iteration. If you see in the next iteration 2, the larger rod is shorter rod in iteration 1, right? Because 84 was basically the shorter rod in iteration 1, but it will become the larger one in iteration 2. And so therefore the value of M will be equals to N. So if we write this kind of assignment M equals to N, that means the new value of M in the left hand side M will be equal to the current value of N. So when I am here The current value of n is 84. Now if I write this m equals to n statement, then what will happen? This 84 will come here and this will become 84. And we will write another statement, new value of n is equals to current value of r. So what is your current value? This is your 18. Now this 18 will become in second iteration the new value of your n. So this will become 18. Now we will calculate the remainder r in the second iteration using this m and n, and this will become what? This will become your 12. So therefore this m equal to n and n equals to r, every time we will use these two statements, and we will then calculate the value of r, which is m percentage n, and if this value is 0, we will say that n is your GCD. If not, then we will repeat again this step, right? That means we will go to the next iteration again. So let us see this thing in our next slide. This algorithm is basically known as the recursive type algorithm. To understand what is recursive algorithm, let us consider GCD m comma n, or let's say GCD 186 comma 84. This is a mathematical function. Let's assume we know what is mathematical function. What is mathematical function? If you write function f x comma y, this is what a mathematical function. Similarly, let's assume GCD, instead of f I am writing a term GCD, and xy is the parameters here, 186 and 84, or m comma n, these are the parameters. In this case the value of m is 186 and value of n is 84. Now if you notice, the GCD of 186 comma 84 is nothing but GCD of 84 comma the remainder, that means 18, or we can say GCD of n comma m percentage n. That means what? To find out GCD of m and n, we are again taking help of the same GCD function but with different arguments. The value of this argument is different. Now it is 84 and 18. Earlier it was 186 comma 84. But the function is still remains the same. What is happening here? The value of xy, if you in a function, sometimes the value of xy may be x1 y1 and other time it may be x2 y2. But see, we are defining the GCD of this with the help of the GCD of something else. So we are referencing the same definition again and again, and this is what known as recursive algorithm, right? So now let us see for this particular example how it actually works. We have already seen that iteration 1, 186, second number this one, and the remainder, the iteration 1, 18. Since it is non-zero, so we cannot say 18 cannot be x, 18 not equals to your x, because this is not equals to 0. So what will happen? In iteration 2, we will first actually execute m equals to n. What will happen? The value of n will create the new value of m, so therefore it will be 84. Similarly, we will write n equal to r. So the value of new n is equals to the current value of r, so 18. Now again we will calculate the remainder of these two, so this will become 12. Again, since 12 is not equals to 0, so 18 cannot be your x, right? Then we proceed to the third iteration. Again this 18 will come here, similarly 12 will come here, and here the remainder between these two will be 6, which is again non-zero, so even 12 cannot be x. So therefore let's proceed in iteration 4. Now 12 will come here, 6 will come here, and now your r is 0. Since this r is 0, therefore this is what your GCD. The moment r becomes 0, at that iteration the value of n will be your GCD. Now let's see it in algorithmic step. This is called Euclidean GCD algorithm. Step 1, read the number m and n. Then if m is less than n, then actually what this means, we are swapping the number m and n. Why we are doing it? Because the assumption in this algorithm is m is always the larger one and n is the smaller one. So while running this program, the user or the programmer may choose the value of m equals to, let's say, 84, the reverse way, and n equals to 186. So then what will happen? This algorithm will not work properly. So before we proceed to the algorithm, we need to swap these two values. We will make m is the larger one, 86, and n is 84. So that's the reason I have added this step. If m less than n, then swap them. That means you just shift the bigger number inside m. Now onwards, we can execute our algorithm. So first you calculate r equals to m percentage n. Now if r is 0, then fine, n is the GCD. But if r is a greater than 0, then repeat step 5 to 7. What is step 5 to 7? First you assign m equal to n, that means this line. And then you assign n equal to r, that means this line. And then you calculate r equals to m percentage n, that means here you will take the remainder between these two and calculate it. Now check this r, if it is still greater than 0, that means you need to repeat again. So you will, if r is not equals to 0, then again go to 5 and continuously execute these 3 steps. Now the moment when your r equals to 0, then you will no longer execute this 5 to 7. You will check that r is not, if this condition violates, that means it will not execute 5, 6, 7 anymore. So let's say we are in step 4. So now your r is equals to 0. That means it will not repeat 5 to 7. It will straightway from here, it will jump to the 8th step, which is print n. And what is the value of n? That is 6. So therefore we actually found out the GCD in this algorithm. Now let us see whether those 5 characteristics of algorithm we are satisfying. 0 or more input, of course we have input m and n. So then next is output, also n should be your output. And and another thing is that finiteness. Of course this algorithm is finite. Now the question is why it is finite. First of all, if you notice the value of all these m, n and r, this is what your m, and then n, then r. See, every time the next iteration, what you are doing, you are assigning the smaller value into the m. That means it will be treated as a longer value or larger value in next iteration. So therefore, iteration 1, if you have a number m, in the iteration 2, the m will have number which is less than the previous, right? Because we are actually assigning the smaller number of iteration 1 into m in iteration 2. So for this reason, m will be monotonically decreasing values. M, if you consider this is a series, see the m is a series and it is monotonically decreasing, right? Now again, similarly, n is also decreasing, right? N is also decreasing. Why? Because you are assigning r to n in the next iteration. Now r is remainder, so iteration 1, the value of r will be always less than both 186 and 84. Both this number will be greater than your r. That is what the concept of remainder is. So in next iteration, the value of n will go to the place of n. So therefore, since the r was the lowest number in your iteration 1, so the value of n in iteration 2 will be less than the value of n in iteration 1. So this is also decreasing. Now of course, if both of these m and n are decreasing, that means your remainder also will start decreasing, right? So therefore, Since it is a decreasing number, and finally you will hit to the 0. Okay, so remainder cannot be negative, so therefore it will go and stop in the 0. Now two things we have actually at the beginning we mentioned here: m may be greater equals to 0, but n should be strictly greater than 0. Why? Because if the second argument is 0, then when you divide to get the remainder, you will actually get an error. So you need to follow these few important features.
Dear learners, now let us summarize what we have learned in Module 4. In Module 4, we have analyzed Euclidean algorithm and we have seen how it satisfies all 5 properties of an algorithm. There are another methods to solve the same GCD problem. In traditional approach, what we normally do, we take two numbers m and n and find the largest integer starting from 2 up to root over n that divides both the number m and n, and that largest number is our GCD. Now in the traditional approach, if the m is very large, then root over m is also going to be large enough. So in that case, you need to run the loop starting from 2 up to a root m, that means a large number, right? So therefore you need to execute many steps to solve that problem. But if you use the Euclidean GCD algorithm, you might have noticed even though m and n is a large number, but after a few iterations, the problem will be reduced to a much smaller problem, because in the later iteration we take the remainders as n, so therefore it will drastically reduce the number of steps. So therefore, as far as the efficiency is concerned, the Euclidean GCD algorithm is much more efficient than your normal traditional algorithm. And in our last module, module 1.2, we have seen two different approach for solving the square root of a positive number. So, and we have also seen the traditional approach is less efficient than the Babylonian search method. So we used Babylonian search method for that reason. One thing that you should notice, a problem could be solved by many different algorithms, but for us the main important thing is to find out the efficient algorithm which satisfies all the 5 properties. So in your assignment we have given you lots of problems. Some problems are new problems. So while solving those problems, please try to investigate the method by analyzing it in all different ways, so that your final solution become very efficient. Now, what next? In the next module, we will see how we can use a computer which can execute the steps of an algorithm. We will formally introduce the concept of programming language in our next module. Till then, enjoy your learning and stay safe, stay healthy. Thank you very much.